Hello, welcome to this presentation on a practical and integrated approach to heat treatment simulation of steel casting. This was originally presented in a virtual faculty development program on simulation techniques for castings and other processes at MS Ramaya Institute of Technology, Bangalore, and IAF Bangalore chapter on 14th of August 2020. We will first look at the challenges in quench heat treatment simulation. Modeling preheating in furnaces is not something to be ignored, as there is a big potential for energy saving in industries. Effective transfer time on furnace to quench tank is also important, as the minimum temperature above AE3 must be ensured, otherwise edges cool faster than surfaces and there can be non-uniform hardness at the end of quenching. Modeling microstructure evolution during quenching is a big challenge. It must be a compromise between equilibrium and TTT diagrams. Heat transfer during quenching is another important phase where quenching is associated with two-phase heat transfer, not properly quantifiable. All three phases present simultaneously: film boiling, nucleate boiling, and convective heat transfer. Development of proper tools for measuring HTC or heat flux rate during quenching. Measurement of HTC in plant conditions is a major challenge. Modeling hardness of quenched structures varies with composition and quenching rates, a property defined by the process route, not just by the composition. The most important aspect. You have to follow the process as it cools down. The final stage is not does not reflect the final properties. Stresses, cracks, and distortion are also important to simulate. So material characterization at high temperatures. Elastic, does it behave elastically, plastically, viscoelastically? So these are the issues and challenges in quench heat treatment simulation. Modeling tempered hardness is effect of both time and temperature also have to be modeled. Now first let us begin with understanding the basic metallurgy of steels. All metallurgists are familiar with the iron-carbon equilibrium diagram, but it is not of much use to modeling heat treatment because the iron-carbon diagram is an equilibrium diagram. Steel is a multi-component alloy, and the equilibrium diagram is a binary diagram, so there are many compromises made. The effect of other alloying elements are considered through defining a carbon equivalent. There are many formulae for carbon equivalent. All these things make the equilibrium diagram not a very good or not a very convenient source of modeling austenite transformation. So we generally go to the TTT diagram, which provides basic information for modeling heat treatment. It shows non-equilibrium phases as against the equilibrium phases in the iron-carbon diagram. Again, it is an isothermal transformation, which is practically impossible, a point that has to be stressed. Now, the generally available or published data is only grade specific, but the individual elements may also affect, and for this purpose, TTT diagrams can be calculated from first principles. For that matter, JMAT Pro software is one of the source for computing TTT diagrams given the basic composition. Thus, neither iron-carbon equilibrium diagram nor the TTT diagram can be independently used for heat treatment simulation, for both have deficiencies. We need to use the information from both diagrams and develop an appropriate diagram for tracking austenite decomposition. Now let us look at this. What are the critical temperatures? We have to get the data from TTT diagram onto iron-carbon equilibrium diagram. Now these critical temperatures mark the beginning and the end of the phases that finally we observe in the heat-treated steel. For example, given any carbon equivalent, you draw a vertical line on the iron-carbon diagram. It intersects the AE3 line, which marks the beginning of austenite transformation into ferrite. The next important temperature is AE1, where the remaining austenite has got the eutectoid composition, which is nearly 0.8. The next important temperature is what is known as the binary transformation ending. And then you have got the ferrite end, then you have got the martensite start, martensite finish. All these three are very, very important temperatures which mark the beginning and end of the important phases. Now, how to obtain these temperatures? Can we read it out from TTT diagram or the iron carbon diagram? It's not possible. So it's not a very straightforward question. So AE3 boundary was obtained by a standard regression equation which is available in the literature, which is a function of all the components of the steel. AE1 temperature for the steel was read off from the TTT diagram for the steel grade. BS, FN, MS and MF were all obtained by TTT diagram. You have got the austenite and ferrite between AE3 and AE1, ferrite and perlite between AE1 and BS, ferrite and bainite between BS and FN, and bainite only between the ferrite end and martensite start, and finally the martensite transforming between MS and MF temperatures. Now we go to the austenite transformation models. Now that we have fixed the critical temperatures, we have to go to the austenite transformation models. Austenite to ferrite, perlite and bainite transformations are diffusion controlled Johnson, Mayle, Avrami, Kolmogorov equations, which are explained in this fashion. Austenite and martensite is a diffusion-less. It's not the Koisten and Marburger equation. So these equations are embedded in our software. Then you have to generate the continuous cooling transformation diagrams from TTT diagrams as the steel cools down from the quenching temperature to the room temperature. You say it has to track the temperature, and as the temperature changes, you get different start and finish temperatures. So Scheele's additivity rule for making transformation begin is used in this case. Real fraction transformed is computed by this formula. The shift, the beginning and the end of the transformation start and end curves are obtained in real time as the temperature is recorded during quenching. Steel property models can be done in different ways, and you have got volumetric specific heat as a function of temperature, specific heat of all steels, volumetric enthalpy, latent heat. All these are functions of temperatures as depicted in this diagram. This is taken from the literature. There's also a possibility of generating these specifically for particular steels, which makes it that more complicated. We will now brush through the input on steels that are required for heat treatment of simulation. It's a summary. Correct interpretation of critical information, that is critical temperatures, AC3, AE1, ACM, CE, etc. are important. Reconciliation of equilibrium and TTT data on steels to obtain these temperatures ranges. Then composition specific TTT diagram, if not at least grade specific, which are available in public domain. Distinct regimes of ferrite, perlite, bainite and martensite transformation, especially in the case of high alloy steels. And an algorithm to track austenite transformation as the steel cools. Generate CCT curves. Now, it is important to note that every point in the steel component will have a different CCT curve. Now, let us spend some time on heat transfer during quenching, how complicated it is. Now that we have understood the steel aspect of it, the complications on the steel, understanding of the metallurgy of steel, we will now go to the sister phenomena, which is heat transfer during quenching as you quench it. Now, this shows cooling curve and the cooling rate curve. The cooling curve is obtained by simple temperature measurements. Austenite transformation depends on the rate of cooling rather than the actual temperature. The next thing is to observe, to appreciate that in all the three phases of boiling, all the three phases of heat transfer during boiling, one is called the film boiling phase, which is at the upper temperature region between, say, from the quenching temperature of 850 to 650 degrees centigrade. And then the middle aspect is the nucleate boiling phase, where you have got the maximum cooling rate, and you will see that the temperature drops off very fast during nucleate boiling. And then you have got the convective phase once it drops down to a quiescent phase of heat transfer. For simulating quenching, we must know the heat transfer coefficient during quenching. Boiling heat transfer is one of the most complex heat transfer phenomena to quantify, as we have explained. A new tool, reference quench probe, has been designed to measure the heat transfer coefficient during quenching in the plant. It is designed for portability and in situ testing. Boiling heat transfer cannot be easily measured or calculated using CFD. It's a two-phase heat transfer. We use the temperature data as input and calculate the heat flux rate. This is known as the inverse heat conduction problem. So essentially, the input to the inverse solver is in terms of the temperature time diagrams as the specimen cools down, and the output from the inverse solver is the heat flux, the boundary heat flux. Now, knowing the boundary heat flux and the boundary temperature, you can find out the HTC and develop the model for inputting to the software. We will now come to the third phase, estimation of quenched hardness. C25, EN8, EN19, EN31, and EN24 were taken as specific grades. We used the Jomini test. The measured hardness and the computed hardness was very well matching for the entire range. The tempered hardness, where the tempering time and the tempering temperature both affect the final hardness, assuming we start with 100% martensite. The tempered hardness is the sum of hardness for the base iron carbon alloy plus the contributions from all the following elements like manganese, nickel, chromium, molybdenum, vanadium, etc. So model integration and features of simulation software, we will spend some time on it.
PMMFE-HT uses the JIT pre and post processor for generating mesh, specifying heating and quenching conditions, material data, and viewing the results of simulation. Solid model of the component may be imported from other software like SolidWorks, STEP, etc. It can also be generated within JIT. Preheating conditions, furnace temperature profile during soaking, and cooling conditions during quenching, heat flux, are input using the wireframe model of the component. The software has unique features whereby the user can input the exact quenching conditions of the component. The heat flux is measured in the plant for accurate simulation and input in the form of a mathematical equation. Thermite Solutions has developed a new tool, a reference quench probe, for measuring heat flux in the plant. A typical heat flux model is shown here, derived from plant data. Refer technical manual for details on how to obtain a regression model based on plant measurements. An advanced model of heat flux during quenching can also be developed for more accurate results. Advanced models for heat flux during quenching have been developed when the surface temperature varies largely just before quenching. These models are developed by measuring heat flux when specimens are quenched from different initial temperatures. The steel grade is selected from the database of steels, which is a part of the software. Simultaneously with the selection of steel grade, its composition, critical temperature, and TTT diagram are loaded. Other properties are also input at this time. Reduction in elastic modulus with temperature is modeled from published results. A typical reduction ratio in the Young's modulus of steels with temperature, giving its ratio at room temperature to that at elevated temperature, is modeled from the literature data. User may input their own model parameters. Similarly, reduction in yield strength with temperature is also modeled as a ratio at room temperature to that at elevated temperature. User may again input their own model parameters. Thermophysical properties, density, specific heat, thermal conductivity as functions of temperature and phases are common to all steels and loaded at the time of assignment of steel grade. The software takes into account the latent heat liberation during transformation of austenite into its product phases. The last step in pre-processing is the process data input. This set of data gives the user a feel for the effect of process variables like soaking temperature, etc. on the hardness, phase distribution, and stress distribution at the end of quenching. A view of the solid after meshing and pre-processing. The pre-processed data is written in a specific format and submitted to the solver. The solver is indigenously developed. which keeps track of the austenite decomposition into its product phases as the component is quenched. Extensive lab trials have shown that the computed hardness at the end of the quenching period is within plus or minus 2 RC. The test distribution is also computed. All the simulation results are then exported back to the JIT post-processor. A typical display of hardness distribution, Martensite distribution, binary distribution, retained austenite, the stress distribution, and the temperature distribution along with cooling curves at any point. Extensive lab and industrial trials using 10 steel grades and 6 quenchants have shown that the hardness prediction is within plus or minus 2 HRC.
We have tested this in plant, that's the ACE carbonite riders in Pina, automotive axles, Bharat earth movers, Bharat Forge, Caterpillar, HAL, Indicab, L&T Hajira, LVM, Mahindra Forge, NBC bearings, SKF bearings, SSS springs, Tamil Nadu heat treatment, fettling services also. All these are our customers. So essentially the heat treatment simulation software is designed with the plant engineer in mind, with the theory of heat transfer and metallurgical transformation working totally in the background. So it integrates all processes during heat treatment from preheating to tempering. The interface ensures smooth running of the software with inputs in practical terms. A robust algorithm combining features of both TTT diagram and the equilibrium diagrams have been developed. Reference quench probe is for both in situ and lab versions, indigenously designed, developed, and tested in industries for measuring heat transfer coefficient, heat flux rate during quenching. Heat transfer coefficient measured in situ based on coupled inverse heat transfer and austenite transformation models is a unique feature which we offer. Model of HTC specific to steel and plant conditions used for simulation for ensuring hardness estimation within 2 to 3 HRC. Surface cooling effects during transfer of large components from the furnace to the quench tanks are considered. Apart from end-to-end simulation on TMMFE can be used for troubleshooting, selection of quenchants, defect elimination, improving stacking efficiency, monitoring of quenchants, etc. We can also save energy during preheating by optimizing of soaking time. 2 specialized modules tested extensively in laboratories and industries to quench heat treatment. Helps to understand and optimize the heat treatment process. And for both metallurgical engineers in industry and researchers in process engineering and mathematical modeling. So this is the summary of our software. It has been an unending journey for me into software development, equipment design, and a never to lose hope attitude in the past 37 years. I could not have reached this stage but for the support of Professor Prabhakar, IIT Madras, for initiating me into FEM software development way back in 1983. My research students, Mr. Abhay Simha, Babu, Arun Kumar, Srinivas Rao, Kamath, who validated my algorithms by experiments. Professor Narayan Prabhu for the challenges he has thrown me and with whom I have shared many conference platforms. My associates, Mr. Raghunath, M.N. Jayant and Arjun, at the initial stages of the company formation. Professor Bernardo of Mexico University for his collaboration with experiments. Professor Roshan of Maynard Steels of USA for the many discussions and his probing questions. So thank you very much for your attention.